Is it good? Okay, let's get rid of this thing also. Okay, all set. Okay. Okay, let's get started. I think today I'm going to continue what I started last time on memory-centric computing. Probably we will see some papers related to this. We haven't released the paper list yet, but we will do so. And we will decide when to start the presentations because we're waiting for the, let's say, attendee list for the course to settle. Hopefully that's settled. How many people are here taking the course? Okay. How many people are online? I cannot see online people. Maybe on Zoom. Okay. Okay, let's get started, I think. This is just to jog your memory. I'm going to have a lot of slides to jog your memory. Basically, we're talking about the memory problem, and we've been talking about how to design more memory-centric systems to solve some of the technology scaling issues like RowHammer, RowPress, etc. And then we start talking about how to design memory that can perform computation. And these were some motivating slides that we used. Is it too bright over here? Maybe, okay. Maybe we turned off. And with this beautiful room, everything turns off. It's okay. I think this may be better for now, right? Otherwise, it looked too bright. And we talked about two types of processing in memory: processing near memory and processing using memory. Near memory means that you have logic and memory that are separate from each other and separately designed, and you put logic closer and closer and closer to memory structures. And we've looked at different examples of that. Today, we're going to cover especially using memory part, but just to jog your memory, near memory. If we have time today, I will talk about some of these real systems that are already out there, and some more real systems exist. But last time we talked about using three-dimensional integration to put logic near memory, such that you can execute some important applications like graph processing or machine learning better, just to jog your memory. These are the graph processing engines we designed, showing significant performance energy improvements, both at the same time. And we also talked about doing machine learning inference by designing accelerators that can cater to different types of machine learning models and different types of layers in machine learning models, which have significantly different characteristics in terms of both memory size and capacity requirements, as well as memory intensity requirements, arithmetic intensity requirements. We said that basically because of the huge variation, it makes sense to design different accelerators catering to different parts of the workload. And we discussed that. We showed significant performance energy improvements also. So memory-centric accelerators can significantly improve performance, as you can see. And we talked about large language models. I'm not going to talk about these again, but you can read some of these papers. In past incarnations of this course, some of these papers were presented. I don't know if it'll happen this time, but let's see. Okay. And there are a bunch of other examples that I'm not going to talk about. I kind of mentioned that this long paper that we've been writing has a lot of these already described. Okay, and then we started talking about processing using memory, and this is fundamentally different. Here, you use the analog operational properties of memory to perform computation. Essentially, you're really exploiting the characteristics of memory to do computation instead of designing specialized logic. And here we were discussing processing using DRAM techniques that essentially enable at low cost analog computation capability. And we were discussing two primitives, basically. If you consecutively activate multiple rows, you do data copy or data initialization. Or if you concurrently activate multiple rows, you perform computation. And this is true even in commodity off-the-shelf DRAM chips. And we saw some examples. I discussed, for example, the importance of data copy and initialization. This is a paper from Google that we discussed last time that showed that in their data center, only 2 function calls occupy about 5% of their execution cycles, which is a lot. And they're related to data copy and data movement, as you can see. And we discussed that if you actually have two pages, and if you want to copy one page to another page over here, going through the CPU is not the, let's say, best way to do this. Instead, if we can just do this in memory, we can significantly improve performance. And we've discussed how to do that. I'm going to skip these because we discussed a lot of this. So if you have a DRAM subarray that looks like this, two-dimensional array of cells, and if you want to copy one row to another row, the key idea of this work that we call row clone is to activate the source row, which brings the data into the row buffer. Now the row buffer is actually a set of sense amplifiers. It's amplifies the data inside the cells that are not very strong. And if you actually activate the destination row after this, which implicitly deactivates the source row and connects the row buffer to the sense amplifier, connects the sense amplifiers to the row that you're activating, you essentially copy the data from the source row to the destination row through the sense amplifiers, through the row buffer. So by doing 2 consecutive activates in DRAM, you can do this copy, bulk copy, easily. And it's negligible hardware cost. In fact, in existing DRAM, if you violate the timing parameters, activate the activate timing parameter, you can do this copy very reliably in almost all the cases. Ismail has some new results probably. He may talk about later on. He's been doing a lot of these real DRAM chip experiments with our lab. Okay. And this significantly improves performance and energy consumption. This is if the source and destination are in the same subarray, you get more than 10x reduction in latency and more than 70x reduction in DRAM energy. Now, if the source and destination are in different banks, you get still reduction because you move the data across different banks, and there are some mechanisms that I'm not going to discuss, but it's described in this paper. If the source and destination are in different subarrays in the same bank, then it's people have developed, including us, have developed other mechanisms to improve that performance energy. So you can actually do a lot of data movement inside the DRAM, and this is actually useful for computation also because you may want to reorganize the data to perform computation inside the DRAM, and having the data movement capabilities inside the DRAM is very useful for that sort of computation. So there's more work to be done in this area, I think. Okay, so we also discussed how to do computation, and this is one way of doing computation in DRAM. If you have 3 of these rows, A, B, C, I'm showing you 1 bit in each row, and I'm showing you the sense amplifier over here, the capacitors and the access transistors and the bit line and the bit line bar on the other side. If you concurrently activate these 3 rows in DRAM, what happens is, based on circuit principles, these 3 cells share their charge with the bit line, and bit lines that are reference voltage to begin with, and they perturb the charge in the bit line, assuming perfect circuitry. If at least 2 of these cells are charged, the result will be perturbed to the positive side. Basically, there will be positive charge shared with 1.5 VDD, and then the sense amplifier will amplify that signal. So if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So the final state that you get by concurrently activating these 3 cells is a majority function of these 3 cells, if you represent the charge state as 1 and discharge state as 0. Okay? So it's bitwise majority function, which is good. Basically, we're representing charge in a logical way, and we're doing computation on the logical values that are assigned to the charge, right? It's still analog computation that's happening, but in the end, we're interpreting it as a logical value. Okay? That's interesting to think about. And if C is set to 1, you get the OR of A and B. If C is set to 0, you get the AND of A and B. So now you have on, AND, OR, and majority. What's missing is NOT, as we discussed. If you actually have the NOT, or inversion, of a cell or an entire row. If you activate only one of these rows, you get the complement of the cell on the other side of the sense amplifier. In this paper, we propose an expensive method to actually put this back into the same subarray. But there later works actually develop better methods. So there you actually already have the NOT as well. NOT is the inversion. And if you have NOT and majority, that's functionally complete. Right. Now you can actually think about your you can think about any algorithm and try to implement it with this sort of execution model. Of course, this is a block bitwise, meaning whenever you're doing an operation, you're doing it on the entire set of cells that belong to a row. Right? A row may be 8 kilobytes or 16 kilobytes. This fits nicely whenever you have a lot of data that you're operating on in a bulk bitwise manner. And there are some applications that actually very much fit for this, like databases, bitmap indices that are used in databases. Some web search engines are designed to do a lot of bitwise operations. For example, if you actually have a database, you can represent presence or absence with 1s and 0s with a particular query. For example, you can present, you may have 8 billion entries, and you may describe presence and absence of that particular entry in a country with a 1, and you can have different columns for different countries, right? So these are bit vectors specified for different countries. Each bit vector is 8 billion entries, and you have ones and zeros. And then you can run queries that say, find me all of the people living in country X that are older than 50, etc. Right? All of those are bitwise operations if you represented your database nicely. Okay. This makes the database size potentially large, but the query is much faster because you're really operating on bitwise entities as opposed to doing more complicated computations. So people have designed web search engines and databases that operate that way. A lot of encryption algorithms, sequence mapping algorithms, set operations also do this. And we've shown that you can get significant performance improvements if you actually take a database that's designed, bit-weaving database, and implement it on top of our simulator that can simulate this, what we call ambit essentially. And this is the paper. Now the question is, how easy is it to, this is where we actually kind of stopped, although I didn't provide a lot of detail on ambit. Now we had a little bit more detail. So the question is, of course, how do you actually implement things on top of this sort of substrate? And programmability becomes very important actually, especially processing in memory, because it's a different kind of execution model, if you think about it in this case. How do we actually take advantage of the existing model and merge it with this sort of execution model? That's what we try to do in this work called SIMDRAM. Essentially, what you're doing is bitwise operations. Any operation that requires multiple bits needs to be done in a serial manner. Right? For example, if you want to do a 2-bit addition, you need to do it serially. You need to lay out your data nicely such that you operate on the first bit and then the second bit next. And then you can keep accumulating things. You need to basically design your layout as well as operations such that you can do things bit serial. In this work, in SIMDRAM, I'll give you a very high-level overview. You can express any operation actually, as long as you express it using this sort of logic and or not logic, like a hardware designer. We can take that. It could be a matrix multiplication, right? It could be pretty complicated matrix multiplication where each entry is 32 bits. Nobody wants to do that these days because 32 bits is expensive, right? But each entry could be 4 bits. And then you actually design the hardware circuit. And we use some electronic design automation tools that are actually developed for some superconducting logic, because some superconducting logic does majorities really nicely. And we optimize this program such that we reduce its latency. And then we have a pass that turns that majority inverter graph into commands in DRAM, basically row clone commands, triple row activation commands, consecutive row activation commands, etc. So that you can actually satisfy what the circuit is doing. Okay? Majority and not, basically. And this program is stored with this new instruction that we add into the instruction set architecture. For example, it could be a convolution, right? Whenever you get convolution that is compiled into the program, it's essentially just like any other sequential instruction, except this gets recognized and shipped to the memory controller, and the memory controller executes this micro program on the memory side and returns the result. So that's the idea, basically. You can still keep the sequential programming model that people are used to and add these operations that are executed on the memory side. Okay, this is an example of what we had called PIM-enabled instructions in earlier work in 2015. This is a PIM-enabled instruction, and you can also decide where to execute it, right? That's another option. Okay, so that's the framework over here. So this way, you can implement any operation as long as you specify an instruction corresponding to it, and as long as you have a micro program that implements in the memory controller. So any operation can be implemented in the memory controllers. In that sense, it's a pretty powerful substrate, right? Of course, some operations may be very slow, some operations may be very fast, and also parallelism matters over here. So if you're doing, for example, 64-bit divisions, this paper shows that it's very slow. Right? You don't want to do very high bit width divisions or multiplications. Even additions are not good because it's bit serial, right? You get throughput because you're doing lots of operations bit serially on many values, assuming your program is doing that. But your latency is proportional to the bit width. And the paper describes linear as well as quadratic proportionality depending on the type of operation. Okay, so this paper also evaluates things with some applications and shows good results also, so that's good. Any questions? Okay, hopefully this is interesting. This is kind of a history of how processing using memory has developed in recent years. And we published this in 2021. Today we're in 2026. There's more to be done in this area. But more recently, this work called MIMDRAM fixes some of the issues. So SIMD is single instruction, multiple data. MIMD is multiple instruction, multiple data. In this work, we tried to solve some of the other issues related to this block bitwise execution and to make it more flexible. And one of the key issues in this sort of block bitwise execution is what is the granularity of execution? Meaning, whenever you do a triple row activation, how many bits are you operating on? Is it 64,000? What is the size of the row, for example? In prior work before MIMDRAM, the size of the row was the granularity. If it's 64,000 bits, if it's 64 kilobytes, it's 64 kilobytes of data that you're operating on in a bitwise manner. Right? If it's 8 kilobytes, it's 8 kilobytes. Both of these are very large numbers, actually. Whenever you do, let's say, modern compilation, compilers have difficulty finding these very large vector widths. So, for example, if you think about Intel AVX, these vector extensions that Intel has, the maximum bit width they went to was 512. They didn't go beyond that. So a lot of compilers were designed to extract bit width of 512, for example. Right? So, but there's a mismatch over here, essentially. So to get rid of this mismatch, this paper uses or proposes using fine-grained DRAM. This is a separate idea. It's an orthogonal idea, but it helps actually processing using DRAM. The idea is, as opposed to operating on the entire row, operate on a fraction of the row, a small part. And DRAM is actually designed in a hierarchical manner where whenever you activate one row, you're actually activating a lot of mats. These are called mats in DRAM. And each mat can be of 512 bit width. The reason you design it that way is because you need to actually have word line drivers that can power, that can be reliable enough to activate the entire row, let's say. So you actually have multiple mats. Instead of basically activating all of the mats that belong to a row, we use what is called fine-grained DRAM that is designed to activate only a fraction, maybe one mat, maybe two mats. In this case, we make it flexible. So that's the idea. If, for example, your program requires only two mats to be activated, let's say 1024 bits to be operated on, 1024 different values to be concurrently operated on, you activate two mats, okay? So only access the DRAM mats with the target data. This improves the utilization, or what is called SIMD utilization, because you don't need to activate all of the other mats that belong to the same row. And to be able to do this, of course, you need to have a mechanism to enable this. People have looked at segmented word lines, for example. If you want to activate only these two mats, you stop the signal over here with some sort of isolation transistor, some sort of isolation, essentially. Now, the good news is if you do this, maybe you also enable the other mats to be able to execute something else, some other operation, right? So you activate these two mats to do operation X, you activate these two other mats to do operation Y on different data. That's why it's called MIMDRAM, you know, multiple instructions, multiple data, concurrently executing on different parts of the different mats, essentially. Okay, so how do you implement this fine-grained DRAM? This is actually an interesting area of research also. There's a lot of work in this area. This is one of our recent works that Atabak has led. He's not here. He was in the previous class, kind of disappeared. Maybe he doesn't like you guys as much. I don't know. Oh, okay, he was answering questions from students. So we teach the digital design and computer architecture, so maybe he's stuck there now. Yeah, the sector DRAM describes a way of changing the DRAM architecture such that you get a more fine-grained access. And there are reasons to do this that are independent of processing using memory. One reason is you want to get only one bit from DRAM, let's say. That's the bit you care about. Today's interfaces don't allow you to do that. You need to get much larger granularity, which wastes energy. So if you want to get only one bit, you're really activating the entire 64 kilobyte row, assuming it's 64 kilobytes. Basically, you're really accessing 64K minus 1 bits for no reason, assuming you don't have a very good locality, let's say, even you don't have any locality. Right? So that's the problem that these fine-grained DRAM architectures are trying to solve. How do I activate as little as possible in DRAM that matches my locality characteristics? Right? So in this case, that's also true. In this case, how do I activate as little as possible that matches my computation characteristics, right? Maybe in this case, we're doing computation. Our goal is not just to access memory for locality purposes. We're not going to cache the data. We're just doing computation. Okay. So there's some other proposals in this work that I will not necessarily go into in detail, but this work adds some low-cost interconnects. This work changes DRAM basically, so that it's more amenable to computation. That's a very good direction because DRAM is not designed for computation today. This work takes one of the steps to revise the hardware or rethink the hardware relatively little. There's more to be done in this area such that it's more amenable to computation, right? One of the computation primitives is if you need to communicate data values, for example, if you don't want to do aggregation or reduction across data values that you take from different mats, how do you actually do that? In today's DRAM, there's not enough interconnects to enable that sort of reduction operation. So this work actually adds that interconnect to do that. And I'll let you read the paper. And there's more to be done in this area because the connectivity inside the DRAM is not good enough for computation and exchange of data across different mats, subarrays, banks, whatever structures you have. And the reason is the mindset of design of memory chips is not for computation, right? People designed it to get data out, not do computation. So there's a huge opportunity to rethink how we design these chips to do computation as well. Okay, so this work also develops a compiler or adapts the LLVM compiler to essentially compile directly to DRAM without changing the programs. So that's one big upside of this work. So it does actually hardware changes, but it also actually does software changes to directly compile. And this also is eased because of the hardware changes, because what we do is we really use a vectorizing compiler, and the compiler automatically figures out which loops can benefit from vectorization. The programmer can do that also and rewrite their programs, which to make the compiler's job easier, of course. So a compiler automatically vectorizes the code, and it matches the code to the vector width, 512 bits, at least the smallest vector width for each mat, but it could be larger also. But it makes it easier because existing compilers can compile down to 512 bits. And essentially, it eases the programmer burden. So this is what the compiler does. Again, this is all open source. You can find it online. And I suggest improving this as much as possible because there's more work to be done in this area. So transparently to the programmer, it extracts vector parallelism or SIMD parallelism from an application and schedules processing using DRAM instructions while maximizing utilization in the different mats you have. So it identifies code, it does code scheduling and data mapping, and it also does code generation such that programmer needs to do, doesn't do any of these. So because of this, it's also limited to the workloads where this is possible to do, right? Not all workloads are amenable to automatic vectorization, for example. You may need to rewrite some of them. So this is actually, there's more work to do in this area. On those codes where things are very nicely amenable to vectorization, the performance and energy results are very significant compared to CPUs and GPUs because you can actually, first of all, you reduce the data movement, and you're also exploiting the huge parallelism that you have in the memory areas. In most of these workloads, we're assuming that, well, or the code is compiled such that the entire DRAM module, all of the bits inside the DRAM module can actually operate on the data, right? Which is not as easy in processors, if you think about it. Okay. Any questions? So now you're close to the state of the art right now. There's a lot more to do in this area, but this is actually a work that's not easy to do. You're changing hardware and the software at the same time. So Geraldo did this work. It was part of his thesis. He did another work. This is Proteus. I'm not going to talk as much in detail about this, but this is really the state of the art currently in processing using DRAM. And what this does is this realizes that there are some other issues in processing using DRAM, and this is the summary slide that I have. Essentially, there is a bit serial execution model, and it's usually employed naively because you have a rigid and static data representation, and you have some throughput-oriented execution, and you have some scalable challenges, especially when you have high precision operations. And this work tries to overcome these challenges. To be able to do that, it actually has multiple mechanisms. One is bit precision. So it identifies operands, narrow-valued operands. So if, for example, some of your operands, the values don't exceed a number, you can represent it with fewer bits. People have used this idea to save energy in microprocessors in the past. Here, we're using the idea to actually improve throughput as well as save energy. So if you can actually identify these narrow-valued operands, you can dynamically adjust the precision with which you operate on those values. And also at the same time, you choose and use the most appropriate data representation arithmetic algorithm implementation. So this work observes that different values and different kind of, essentially different widths benefit from different types of adders, for example, addition algorithms or multiplication algorithms and data representations. Some of them, for example, are better represented with the redundant binary type of data. Some of them are better represented with two's complement. And depending on the width of the data and the complexity of the algorithm, there's a mechanism to choose which one is the best for a given processing using DRAM operation. So there's a lot of software mechanisms to choose. And in the end, it demonstrates that it's better than the previous work. And you can take a look at that. So there's more to do in this area. I think one of the interesting things that this work shows is that different kind of data representations are better for different kind of operations and data bits, right? In processing using DRAM. So we should not assume the same data representation that we assume for CPUs today, for example. Even CPUs actually assume some data representations, and that has been questioned more recently because of the computation operations that are done on matrices, right? People develop new data representations. Floating point is too expensive. Let's do brain float, different kind of things. And that should change also. In processing using memory, I think there's more to do in this area. Any questions? Some people have ideas? Okay, not yet. This was an interesting paper because normally after you revise a paper and you satisfy all of the requirements, those papers get accepted. But these reviewers decided to reject the paper, even when we satisfied all of their requirements. I joke with Geraldo that his paper was one of the two papers that had this distinction of being rejected after satisfying all the requirements. But this is not nice, clearly. Okay, I have a lot of these stories, as I said. Okay, so let me switch gears a little bit and say that this is all theory, right? If you think about it, all of this is in simulation, and we assume that we could do these operations in DRAM chips. And that's actually been some of the criticism, including unfair criticism of this work. In fact, at the Ambit paper that introduced these bulk bitwise operations got rejected 4 times before it got accepted. And one of the major reasons was DRAM manufacturers will never implement this. If I have time, I'm going to show you that comment. It's an interesting comment because you write this scientific paper, you do all of this work to demonstrate that this may be a good idea. And the comment is, reject, DRAM manufacturers will never implement this. It's good to think about this. I mean, does this make sense as a scientific review? It requires a crystal ball, right, to basically verify this review. But unfortunately, this is the state of the art in reviewing, and people like this get away with it. And that's part of the problem. They can produce this sort of reviews, by the way. Anyway, we may get to that. So we did also some studies to show that even if DRAM manufacturers will never implement it, even if they do nothing, you can actually see these operations in real DRAM chips. So basically, maybe there's something that's not terrible in our theory, to say the least, let's say. Okay, so basically, existing DRAM chips are quite capable. So we developed this. There was actually this compute DRAM work in Micro 2019. I don't have it here, but that's actually a very nice paper that showed that you could do some of these operations in real DRAM chips. We wanted to actually make an end-to-end prototype to run applications that can do some of these operations, that can offload some of these operations on real DRAM chips. This is actually a prototype that was done in DDR3. There's more work to be done if people are interested in doing research in this area. Basically, what this work shows is by violating timing parameters, in DRAM, you can do row clone operations, and also you can generate true random numbers. These are based on prior works. In one of our prior works, we showed that you can do true random numbers, but you can do these, you can actually employ these in an end-to-end program. So this is the board. We have a RISC-V processor running on the FPGA board. There's an operating system, etc. You can run an application. And what we do is we change the mapping, data mapping in the operating system, etc., to enable these operations that we discussed. Not the computation yet. Computation will come later, hopefully. Maybe Smile is working on it, who knows? Or maybe some other people. Let's see. But the key idea is you change your program such that whenever you have a copy, you have a special copy. You copy one row to another row. And the data mappings are done in the operating system such that you can copy from one row to another row that are in the same subarray. Okay? You need to change the operating system. You need to change the program. Maybe the compiler. In this case, we didn't touch the compiler, but you can change the program. The basic idea is that operation gets offloaded to the memory controller. That's a soft memory controller because we're running on an FPGA. We have a RISC-V core. Whenever it's executing this operation, it gets offloaded to the memory controller, and the memory controller does the copy by violating the timing parameters and then returns an acknowledgement signal such that the core can continue. And you can run an application with this. It's painful, but it's possible to do. Random number generation, very similar. If you want to generate a random number in DRAM, you change the random function call such that when you get to the random function call, it gets shipped to the memory controller, and memory controller violates the timing parameters to generate a random number and returns the result back to the core. Okay? So it's fun to do this, and it should be extended, in my opinion, to other things like DDR4, HBM, and also easy to use. So there's more to do in this area. But we showed that you can actually run real programs. These are some micro benchmark results because it's easier to run micro benchmarks. Real programs still is harder, but it's possible if you spend enough effort. You can see that these are real results when you run initialization and copy programs, and you see significant performance improvements. These improvements are even larger than what we demonstrated in simulation. And the reason is in simulation, in the row clone paper, for example, what we showed was a powerful out-of-order execution processor with caching, a lot of latency tolerance mechanisms. In this particular case, this poor RISC-V processor inside this FPGA board is an in-order processor that doesn't have a lot of latency tolerance mechanisms. So the results that you get by offloading to memory is even better. Hopefully that makes sense, right? So simulation is not necessarily bad, let's say. Sometimes people think it's bad. Okay, there's more on PyDRAM. You can find it out. As I said, this has been 3 years since we published this work. It got its share of rejections, of course, before being published. It's got the, I think there's more to do in this area to develop more. Any questions? Yes, go ahead.
Yeah, so actually, whenever I see slides on video, I find a lot of like huge performance advantages. And like, if it is actually implemented in efficient, then how long does it take?
Well, you never know, basically. It depends, right? Usually, let me give you the example of RowHammer, right? That's a different domain, but these things are not implemented in industry yet. It requires basically changes to the software stack, and that takes longer. But RowHammer, for example, the immediate solutions were implemented very quickly, right? They were not good. They were not that good, but it was implemented quickly. And more recently, standards have changed to include per row activation counters. So it took maybe 10 years to get to a good solution. Maybe. I don't know if it's still good. I'll put good. But solutions were adopted relatively quickly in that case, right? So it really depends.
Because it's really serious issue.
Yeah, I mean, in the end, they thought it was more serious maybe. Here, I think because it's an additional functionality, because in the end, industry implementation has a lot of other concerns, right? Is it the market size? How much money will I make? And then you need to consider, is there an easier way to make money, right? So in the end, they don't consider necessarily what may be the most important thing to consider: energy, sustainability, for example. They're not. These things are not in the minds of people who really manufacture these things, and they have to make a decision, right? They may think about it, but in the end, some decision maker says how much money this is going to make. That's the bottom line, right? So it's good to think about that, right? Even though an idea may have perfect, easy implementation, like row clone, for example, is actually very easy to implement. That has not been, and the idea has been out for 13 years now, since 2013. And it's not adopted yet. I think somebody will adopt it eventually, but it takes time. Okay. Like as I mentioned last time, even subarray level parallelism, that's also an idea that actually improves performance. And Samsung and Intel, they both independently verified that this is a good idea. We published in 2012. They pushed it very hard to get it standardized in JEDEC, and they were not successful. These are two huge companies, if you think about it. And the idea is does not get adopted. But that paper has a lot of influence because everybody says you should do subarray level parallelism these days, actually, which is interesting. Do you agree? Yeah. So you can see that there are a lot of other issues here. Yeah.
How many percent the new papers are actually implemented?
Say it again? Oh, I don't know that number. Yeah. That's a tough one. And it's not the same in all areas. But for example, today, machine learning area produces thousands, tens of thousands of papers. Many of them are not implemented. Many of them will not be remembered, in my opinion. So, you never know, basically. Yeah. And also sometimes you don't know. Sometimes companies implement some ideas and they don't tell you, right? Yeah, it's interesting. Okay. Okay, so Ismail, who is sitting over there silently, has done a lot of work in this area. I'm going to talk about some of the things that he's done. This is also an HPCA 2024. And essentially, real DRAM chips are actually even more capable than what was demonstrated until this work. So in two works, actually, Ismail demonstrated that with real DRAM chips by, again, violating the timing parameters. You don't change the DRAM chip. You don't change anything in the interface. You just need a memory controller that you can change to violate the timing parameters. By doing so, you can copy one row into 31 other rows with almost perfect reliability, success rate. He has a definition of success rate that you can read in the papers, or you can ask him. It's almost perfect, as you can see. Ideally, we want it perfect, so making it more reliable is a good opportunity to do some even bigger work. He has also shown that you can perform the NOT operation with a bunch of output operands, and you can also perform AND, NAND, OR, and NOR operations in DRAM, which is fascinating. Maybe not as reliably, but still, you can do it. And nobody designed these chips with that purpose, right? We're just abusing these chips. We're doing things that the standards tell you not to do, right? They tell you don't violate the timing parameters, but we do violate them. Okay, so just to demonstrate that this is you can do these things in these chips, even if chips are not designed for it. And then our goal is to actually show that if you can actually design things better, you can do even more things, or you can do these things reliably. So this is multi-row copy. It's very similar to row clone. The idea is you copy one row to another row in row clone. Here, you copy one row to many other rows. One-to-many copy, basically. Multi-row copy. And this happens by doing a specific violation of the timing parameters. You can activate multiple rows. It's called multiple row activation. And you can do this consecutively. You call it CoMRA, right?
Yes.
Okay. CoMRA and SIMDRAM. SIMDRAM is simultaneous, CoMRA is consecutive, not concurrent. Concurrent would be bad, right? Okay. So, and you can read the paper to do that. Because what happens is when you do one activation, you get the data value in the sense amplifiers, and when you violate the timing parameters in a particular way, many rows open at the same time, and this data value in the sense amplifiers get copied to many rows. That's the idea. NOT operation, we've kind of discussed this. Basically, you connect rows in neighboring subarray through a NOT gate by consecutively activating rows. You first activate the source row, and then by violating the timing parameters, the destination row gets activated as well, and it gets the value A bar, essentially. It's very similar to what we have done with ambit, except it happens on the other subarray. And I think maybe the most interesting one, although NOT is also interesting, but all of these are interesting, but NAND, NOR, AND, and OR are perhaps the most interesting ones. And the idea here is to manipulate the bit line voltage to express a wide variety of functions using the simultaneous multi-row activation. So if you can activate multiple rows simultaneously, what can you do? this is theoretical picture. If you have, let's say, two cells, A and B, on this subarray, this is the bit line over here, and then bit line bar over here, the other connected to the other end of the sense amplifier and to the other subarray. Let's say you have values A and B and X and Y, cells A and B and X and Y. Now, if you had the primitive to concurrently activate these four, in circuit theory, what should happen is that sense amplifier compares the average voltage of A and B to average voltage of X and Y. And if the first one is greater than the second one, the top bit line is amplified to 1. This gets amplified to 0. And if the other is true, VXY is greater than VAB, this gets amplified to 1. This gets amplified to 0. Okay, that's the idea. That's circuit theory. That's what should happen. And you can now use this theory to put certain values to the reference subarray, which enables a certain computation to be done on the values X and Y. Okay, so for example, if you can initialize the reference subarray voltages to be VDD over here and VDD over 2, assume that you have 3 voltage levels, 0 VDD over 2 and VDD, then the value that you compute in the compute subarray is an AND function of X and Y. And the result that you would get in the, assuming you do concurrent activation, right? You concurrently activate all these four. The result that you get over here would be the AND function of X and Y. And the result that you get over here would be the NAND of X and Y, because it's opposite, clearly. So why does this happen? And there are ways to actually set a cell to VDD. There's another way to set a cell to VDD over 2. It's from another paper, which is a nice paper. Do you agree, Ismail? Yes. Okay. And you verified that you can do this? Yes. Okay. Then you can read the paper to figure out how to do it. So if you set the values in the reference subarray like this, then you get an average of 3 VDD over 4. For the average of X and Y to be greater than 3 VDD over 4, X and Y should be both set to 1, right? Otherwise, the result will be 0. That means that you're computing an AND function, right, over here. And by definition, or by the looks of it, the NAND is computed over here, okay, in the reference subarray. So you get AND and NAND, depending on which subarray you look at, okay? And the OR and NOR is left as an exercise for you guys, but it's not that hard to do. Okay. So this is nice. And the key thing is, this is doable in DRAM chips that allow multiple row activation or concurrent multiple row activation. So that's why we have built, well, this is not the only reason why we have built this, but that's one of the reasons why we're expanding it, to demonstrate that you can do this more, and you can do this hopefully more reliably with some mechanisms. These are the DRAM chips that are tested for concurrent multiple row activation that are supported. So simultaneous, sorry, I say simultaneous. See, you confuse me with your camera thing. How did I not pick up on this one before? Concurrent, camera, consecutive and concurrent share co. Okay, consecutive one. So these are results from real DRAM chips for copying one row to a varying number of destination rows on the x-axis. You can see that, and the success rate is a measure of reliability. You can see that copying one row to n number of rows is quite reliable, even though the DRAM chip is not designed for this purpose. We're violating the timing parameters, right? 99.98%. Have you made this 100% yet, Ismail? Working on it. Okay. One of his tasks in his PhD is to make it 100%. It may be very difficult. It may require some changes to DRAM, but those are okay. Because the key here is, even if you don't do any changes to DRAM, you get 99.98%, right? So what if you actually go and figure out and change DRAM accordingly? Maybe you'll get 100%. Okay, it's good to think about it. And these are results from AND, NAND, OR, and NOR with different number of input operands. And these are for different chips. You can see the variation comes from different chips, essentially. And is it different chips or different rows? All, basically, yeah. All cells, okay. It's all cells, basically, distribution. And you can see that you can perform AND, NAND, OR, and NOR. Sometimes it's not as reliable, but it's still not bad. It's more than 50% reliability, right? Again, the key is the chip is not designed for this purpose, right? We're abusing the chip. And clearly, there are a lot of other circuit level noise effects that we're triggering if you actually do this multiple row activation, because the chip is not even designed to support multiple row activation, right? It's designed to support a single row activation at a time. Okay. Okay. So these are the papers. This is on multi-row copy. This paper also looks at the majority operations. So you can do majority 9, for example. And that can actually enable redundant copying the data and doing the operation redundantly on 9 rows. And then you can actually get better reliability. And this is a functionally complete DRAM that Ismail can tell you more about. Yes?
Can you tell in brief what exactly is violating of time parameters? What do we change and why do we need to violate them?
Okay, why do you need to violate them? So violating the timing parameter, what it enables you to do is, while one row is open, another row also becomes open. Right? You activate multiple rows concurrently. There's no way to do that in DRAM today, because DRAM assumes that you can only open one row at a time. If you want to open some other row, first of all, concurrently, you cannot do that. Consecutively, you can do it, but you need to wait for some time to close the first row, such that the first row is guaranteed to be closed, and then you activate the next row. So our goal in these works is to show that if you can open multiple rows, either in quick succession, consecutively, or completely concurrently, you can essentially get a row clone function copying that we hypothesized exists, or you will get this block bitwise computation that we also hypothesized. Okay, so violating enables you to do that, and there's no other way to do that as far as we know without violating today. Even internally, there's no magic command that enables this, basically, because DRAM manufacturers have never thought of this. Okay. Yes. Oh, there are many, many physical issues, right? Ismail can talk to you more, but essentially, when you violate the timing parameter, for example, one of the issues is that the cells have different levels of charge, right? Not all cells are equal. The circuit theory says that the circuit theory works if cells are of similar size. But if one cell has a lot of charge, if another cell has little charge, for example, the majority function will not work, right? Hopefully that's clear. Because one cell will dominate the activation, right? If you want to get a majority function when you open, for example, 3 rows or 4 rows or n rows, all of the cells should be equal in terms of the charge that they supply, in terms of the impact that they have on the bit line. If one cell dominates, you'll get the value of that cell, for example, not a majority function. That's one example, right? Another example could be you may get cells that are similar with some luck, but maybe the sense amplifier is not able to sense things very well because maybe, I don't know, there's too much charge. Maybe you have some more examples over here. Anyway, these are good things to ask, but maybe that'll be detailed in the next paper. Yes.
First one is that if the error rate is less than 50%, why don't we just repeat it for times?
Yeah. Yeah. Do you want to answer that?
What's the question?
You couldn't hear. Okay.
If the success rate is higher than 50%,
Higher than 50%.
why don't we just repeat it multiple times?
If you repeat it, you might lose. Right? Assume that your accuracy is 90%, yeah, right? 0.9. And if you change that 0.9, 0.9, 0.9, now in the end, if your chain is too long, you will get like 0.1.
What I'm considering, you can just have multiple results, multiple results, and even do a major repeat.
Yeah.
Yes.
I think that's good.
That could solve to some extent. Actually, the other paper actually deals in a similar way.
Yeah, this paper. Right?
Yes.
Yeah. Yeah, there's some in this paper that is similar to your idea. Basically, you replicate your data and you do a larger majority operation, for example, right?
Yes. So one of the issues is your deviation is not that low, not that big. And what you do is you replicate inputs like ABC, 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 ABC.
Now you amplify the difference more, and you do your operation, and we observe that you can actually increase the success rate on average more than 30% in majority.
Yeah. Another question?
My second question is that we are activating, like we are violating some specifications, so maybe sometimes can be unstable. So
That's correct. And that could be one of the reasons why.
I wonder if the success rate differs if the number of events or activities affects the success rate.
Yeah, yeah. So the short answer is I am sure it does, but I'm not sure if we did those experiments. It's good to think about that. So if you actually do a lot more, essentially you draw a lot more power, it's likely that success rate will be affected. But I'm not sure if he did the experiment, but he's talking right now. So maybe later you can ask him. Very good questions. Okay, unless there are other questions, let's keep going. So this is actually very interesting now, right? Because now we can abuse commodity memories, just change the memory controller, maybe even have an implementable product out of this. I think we're not there yet. That's not our goal, maybe initially. Our goal is to show that you can do these things, and even if you don't change the memory. Now, can you imagine what else can you do if you change the memory? So what else did we show? So this is actually one of the earlier works that we published, where we showed that DRAM chips, in LPDDR chips, actually in this particular case, by violating the timing parameters, you can generate random numbers. The idea is if you activate one row, and if you reduce the time, you read the data from that row, the cells do not settle by the time you read from it. So you don't give enough time for the circuits to settle. And you find some cells that actually are flaky for a given time period for which you activate the row. For example, if the activation latency is 5 seconds, this cell will likely fail or not fail. We don't know. With 50% probability, it will fail. And that could be a very nice random number generator. The insight in this work is that find such cells that fail with almost 50% probability for a given activation time and use them as random number generators. So you can find a lot of these cells in DRAM and stitch them together. That gives you a 64-bit random number. That's the idea. And you can do this relatively reliably. So this is also a demonstration of real DRAM chips. Even before that, we demonstrated that actually you can do physical unclonable functions. I guess that's a different slide. That was in HPCA 2018. But later works demonstrated that using concurrent row activation, like 4-row activation or 2-row activation or 32-row activation, you can actually generate random numbers. This is more recent work. I think this is Ismail's work that more recently shows that you can actually do even better than prior works. So it's good to think about that. And we also have some system level works to use those true random numbers. This is a physical unclonable function I'm not going to talk about, but this was actually the original work that showed that by abusing DRAM chips, you can do some useful things. So if you change DRAM chips, you can actually do even more. I'm not going to talk about this also. This requires changes to DRAM actually to do lookup table-based execution. But if you want to do more functions, complicated functions, bitwise execution is very limited, in my opinion, especially if you want to do complicated functions, right? How do you express in a bitwise manner? Lookup tables, on the other hand, could be easier to adopt and easier to do complicated functions because it's a lookup, right? Instead of implementing the function with logic, you're looking up the result. And this work tries to do that. There's more work that builds on Pluto. I like this idea very much. Unfortunately, this also got rejected many times before it got published, which is very sad, I think. New ideas get this sort of, let's say, impact for some reason. Why are we trying to improve DRAM, right? What's the point? This is a real mindset. I'm not joking. And real mindset in academic communities sometimes, which should not exist. This mindset should not exist. People are entitled to their opinions. They can say that, but that should not be affecting the review process. Okay, what about other types of memories? It's also a very interesting question. So we've done work on in-flash block bitwise execution. I'm going to talk about this. And assuming this sort of block bitwise execution in Flash, you can actually build a lot of interesting things like accelerating homomorphic encryption, which is actually a very block bitwise thing to do. Again, some of these papers may be presented. But let me give you a quick idea of this work. Essentially, in flash memory, NAND flash memory, you can also do these operations, except they work in a little bit differently. It's not exactly the same, let's say. The idea is computation on multiple operands happens in a single sensing operation. And you can actually make it very accurate by changing the flash controller to correct the data or to read the data more accurately. So that's the idea over here. In DRAM, we don't have that luxury very well, because in flash, when you read the data, you try to sense the data, and you basically use some read reference voltages, and you can change the read reference voltage, read the data again, and you can keep doing this multiple times. Whereas in DRAM, you don't have that luxury. So the idea is basically similar, concurrently activating multiple rows, enables simultaneous sensing of the bits, and you get a bitwise AND function. So let's take a look at this. Without going into a whole lot of detail on flash memory, which would be a lecture in itself, this is what flash memory looks like. This is one bit line over here. And I'm showing you 4 cells over here. They all belong to different word lines. Essentially, each cell operates as a resistor or open switch. The value 1 is resistor. The value 0 is open switch. And this is a bit string over here. So a bit line reads as 1 only when all of the target cells store 1. Okay? So if you simultaneously activate multiple word lines in the same block, you essentially get a bitwise AND of the stored data in the word lines. Normally, you don't simultaneously activate. You activate only 1. And then what happens is whether that is 1 or 0 determines the output, because everything else is set to 1 essentially in that case. Okay? That's single activation. If you simultaneously activate, what happens is you get whatever is stored over here. And if you'll get a 1 at the end only if all of the cells that you simultaneously activated store a 1, otherwise you'll get a 0. And that's a bitwise AND function, right? So that's bitwise AND. This is called intra-block multi-word line sensing. Okay? And you can also do OR, but I'm not going to describe it. This across blocks, inter-block essentially. Inter-block, they connect to in a wired OR type of manner. As a result, you get an OR function. Okay. I don't have it over here. But essentially, you can do other functions also, because there's an inverse read function that happens in flash already that gives you the NOT. So NOT is actually really easy in flash memory today. So you can do essentially all functions leveraging existing features of NAND flash memory. And we verified this using a bunch of Samsung chips, state of the art at the time. Essentially, you don't need any changes to the cell array. And you can have many operands. You can do up to 48 input ANDs, up to 4 input OR, with a relatively small increase in sensing latency over here. And you can orchestrate this in the flash controller, because you change the flash controller to do this. In that sense, these are operations that how should I put it? Maybe you're essentially not violating things in the same way you're violating a standard over here, right? Because flash controller gets designed together with the flash chip, and you can in the end sell the flash controller and the chip as a product. Right? And there's also a mechanism called basically by programming the cells carefully, you can significantly improve the reliability of computation results. There's no bit error rate that we observed in the flash cells. And these are simulation results after that, because actually building a prototype that enables this is kind of like PyDRAM type of work, which is also good to do, but it may take years to do it, like PyDRAM did. But in simulation, if you can actually do these, you get significant benefits. And this is the paper. And later works actually show that you can improve this. And there's also more to do in this area again. We're demonstrating that you can do some operations in flash. But again, flash memory is not designed to do some other operations, like shifting, for example. There's some other works that looks at shifting. Flash memory is also not good at, again, communicating data internally. So you can actually rethink and redesign flash chips to do more. There's more work in this area also. Okay, any questions? There are also emerging memory technologies that are, I think, important. Basically, those also can do a lot of operations. Essentially, in my opinion, any memory can do a lot of operations. People have demonstrated SRAM can do similar operations. Similarly to emerging memory technology, it's an area that I worked a lot on in the past. Like we worked on phase change memory. We didn't do computation yet, but we wanted to enable it as main memory. And we did the first architectural exploration of it. We wrote some papers. Intel realized in 2018, but later they realized that they don't want to do it anymore. So you cannot buy these easily, at least anymore. At least they're not being manufactured. But this was a main memory technology or phase change memory based main memory that they manufactured and that you could use. How many people have it? Not many people have it. Do you have it? Okay, it's good to have, I guess, but yeah. Anyway, so other works have shown that you can do whatever we envisioned for DRAM, you can do it in PCM also, row clone and bulk bitwise operations. So all of these memories are able to do it. And you can take a look at that paper. But there's some other things that these memories can enable beyond these bitwise operations that are very difficult to do in DRAM. I'm going to mention these. I'll go through this relatively quickly also. And these are called in-memory cross-by array operations. And these are actually, again, purely in the analog domain. It's a little bit different from the bulk bitwise operations, because in bulk bitwise operations, what we're doing is we're treating the analog values in DRAM as digital, right? We're doing the computation in the analog domain, but we're really representing the values, thinking of values as 1 and 0. Here, we're going to really think of values as analog and operate on them. Okay, so basically, some of these emerging non-volatile memory technologies have cross-by array structure, many of them actually. And these cross-by arrays can be used to perform dot product operations using analog computation capability. And you can guess why dot product operations are interesting today, because of machine learning, right? Matrix multiplication. Essentially, you can operate on multiple pieces of data using Kirchhoff's laws. How many people know about Kirchhoff's laws here? You probably had some physics at some point. Yeah, okay. You can raise your hand, don't be shy. How many people do not know about Kirchhoff's laws? Okay, maybe you didn't have physics. You're going to learn a basic representation of it. But basically, the key takeaway is that bit line current is a sum of products of word line voltage times 1 over cell resistance. I'm going to show you a picture of this also. And computation is done in analog domain inside the cross-by array. But you need a peripheral circuitry for digital to analog and analog to digital conversion. So this is actually what Kirchhoff's law says, basically. If you have, so basically current flowing on a wire is the sum of currents that are being contributed to that wire. That's what Kirchhoff's law is actually. So I that's flowing over here is the sum of currents that are coming here, I1 plus I2. And I1 is represented, that's I1 that's flowing through this resistor is represented as V over R. That's basic law of physics, right? Voltage over the resistance is current. In this case, G is 1 over resistance, so it's resistance to the -1. They call it conductance. So I1 over here is V1 times G1. G1 is the 1 over resistance value over here. V1 is the voltage that you apply over here. And I2 is equal to V2, the voltage that you apply to this bit line, word line, sorry, and the resistance of this resistor over here, okay? So basically, the current is summed up as I1 plus I2, which is V1 plus G1 plus V1 times G1 plus V2 times G2, or V1 divided by R1 plus V2 divided by R2. Now, this is nice because what you're doing is really a dot product, right? The inputs are V1 and V2 and G1 and G2, right? You're really taking the dot product of these two vectors, V1 and V2 and G1 and G2. Okay, that sounds good. Now you can generalize it. If you want to, let's say, multiply a vector of 4 inputs with a matrix of 16 inputs, this is what you would do. You supply the vector in the word lines, and bit lines will sum up the currents with the different columns of the matrix, okay? So V1, V2, V3, V4 will be multiplied by G1, G2, G3, G4 in the first column, and also with G1, G2, G3, G4 in the second column, and also with the next column, and then also with the next column. So every column, every bit line will have the analog value of this multiplication. Okay, that's the idea. This sounds good, right? This is a matrix vector multiplier right now, which means that if you're operating on some matrix, you can represent the values as resistances in the analog domain, hopefully by programming this thing. And usually these memories have a way of programming, very much similar to flash memory, but of course different. You can have fine-tuning based programming of these values, and then you supply the vector as voltages, right? And this is the result. That's Kirchhoff's laws, basically. If you didn't know, now you know what Kirchhoff's laws are. And this is how you can represent a matrix vector multiplication. So you will hopefully get the outputs correct. That's the idea. You just need to put the weights, program the weights nicely into this matrix. Okay? So these are all animations that I will skip right now. So for this, you need some peripheral circuitry requirements. You may need to have digital to analog converters. You may need to have analog to digital converters in the end because you operate on analog digital values. Because also it's hard to operate on analog values concurrently. There are a lot of reliability issues over here that I'm not going to talk about, gloss over. But if you can do this, this could be pretty powerful, right? You're not, basically, you're not building a multiplier, right? We did not build a multiplier. We're just taking advantage of the analog operational properties of the circuitry to do multiplication. Very similar to what we have done with DRAM, right? Except I don't know how to do this in DRAM. If you come up with a way of doing this in DRAM, that could be golden. It may require changes to DRAM, actually. I think it will require changes to DRAM. But if you can find a way of doing this with low cost in DRAM, then that could be golden. There's a thesis topic for some people. Okay. So people have shown that you can map convolutions, which are at the heart of convolutional neural networks. Again, I will not go through this in detail, but what you're doing with a convolution is you have an input that's blue over here, and you want to generate an output. Essentially, you're filtering. Convolution is literally a filter. You're passing a kernel, in this case 3x3 kernel, over every single element of the input to compute an output. So you're doing multiplication essentially. Okay, and you can actually do more complicated mapping of input output. This is three-dimensional, as you can see over here, and you keep the weights essentially in the non-volatile memory. So people have done a lot of work in this area. Again, I will not go into details. So clearly you can do multiplication this way, but only multiplication, right? That's the disadvantage. Meaning, what if you have other operations? The beauty of what we had done with DRAM was it's very general purpose, right? It's block bitwise. It cannot do multiplication with large numbers really well, but it's very general purpose. You can implement anything on top of this. With just multiplication, with Kirchhoff's laws, you can only do multiplication, unless someone comes up with a way of abusing more of this. Let's see. So for other things, you need to actually do some other things. So you need to actually add more memory, add more computation units inside the memory to actually do other functions. So in machine learning, there's certainly multiplication, but multiplication is not the only thing. You have some nonlinear operations, for example. For those, if you want to do on the memory side, you need to add near memory logic. So people usually combine processing using memory and processing near memory when they do this sort of non-volatile memory-based PIM. So it's good to think about the trade-offs of these different paradigms, right? Okay, so we've done some work in this area that I'm not going to talk about, but you can take a look at some of our papers. And there are a lot of other papers also that have looked at using, for example, memristors to do this sort of operations that I just talked about, actually, and also some architectural evaluations of it. Any questions? Sounds interesting, right? And a lot of these operate in a systolic manner, so systolic arrays are interesting to look at. Okay. Wow, we already are 5:30. So, okay, I'm not going to cover the backup slides, but I'm not at the backup slides yet. So there's more, and we've covered essentially both processing near memory and processing using memory. It's good to think about the trade-offs between these. In the end, processing near memory enables implementation of anything because you're implementing logic, right? Processing using memory is more limited, as we have seen, but it could be very powerful for those operations that fit it really well. And if you want to do both, it makes sense to do both, of course. And I think the real systems, and also processing near memory is easier to do today. That's why people have been looking at real chips that can do this, whereas processing using memory is much harder to do, to do it reliably. Although the fact that the existing DRAM chips can do some of it reliably, or mostly reliably, even if we don't do anything, is quite encouraging, right? Actually, a lot of DRAM manufacturers were skeptical about processing using memory, because they tend to be conservative, you know. I understand them also. As long as they don't reject papers, that's fine. They can be skeptical. Skepticism is good. I don't have a problem with skepticism. I have a problem with destroying promising ideas that you may not have the good mindset to believe in at that point, right? There should not be non-scientific reasons to destroy ideas. Skepticism is good. And after we published these results that I've discussed on real DRAM chips that abuse DRAM, a lot of them actually thanked us because we showed the capabilities of their chips, and some of them are actually very interested in working with us to do even more. So that's the interesting thing here. Okay, so we've written papers about this. So one of the issues that I would like to discuss, even though I'm not going to go into a whole lot of detail, is adoption. And some of the works that we've described actually geared toward adoption, right? And this is the most difficult issue, perhaps, because you can design any hardware in the end. Although these days, manufacturing cost of hardware is getting harder and harder, especially fancy hardware or fast hardware. But assume that you manufactured, no one may use it because you didn't consider how to get it adopted, right? And that's really important when you're designing hardware. In this case, we're not even designing new hardware, right? We're actually trying to change the paradigm of computation, even bigger in terms of, even a bigger problem in terms of adoption, because people are not used to thinking about doing computation on the memory side, let alone these processing using memory mechanisms that are actually even more different, right? Processing near memory is at least easier because computation, the same computation you do moves somewhere else. That somewhere else happens to be beyond the big boundary, processor and memory, that people have constructed to exist. And that is the adoption issue, that caused the adoption issue. But processing using memory, you're not even used to this computation, right? As much, at least. So there are many adoption issues over here, and usually they're related to software and system levels. So application and software. How do you enable killer applications, important applications? How do you make it easier to port these applications, ideally without any support from the programmer, right? Compiler support, for example. What kind of interfaces can make it easier for the programmer to program for these devices? So there are many interesting questions over here. How do you actually enable system support and security issues? How do you solve any security problems that may come about? Coherence, for example, synchronization, virtual memory, isolation, communication interface. There are a lot of questions over here, basically. How do you enable a runtime system and compilation mechanisms to take advantage of this sort of substrate, processing near memory and processing using memory? There are a lot of issues over here also. Some of these papers actually try to solve some of them, and they're actually not easy to solve, like data mapping is not easy, for example. And infrastructure, because a lot of these decisions that we make today assume processor-centric systems, right? Everything that we have designed assumes that there is this computation is done far away from memory, right? We're kind of breaking that fundamental invariant that people have assumed. And there are good reasons for breaking it, like we've discussed last time, but breaking it also creates these adoption issues that you should not be insensitive to, let's say, if you want your work to have impacts. So designing infrastructures, enabling infrastructures to assess benefits and feasibility is also important, and that's why we've been actually investing a lot on infrastructure. So there are a lot of adoption issues, no question about that, but some things can be adopted more easily than others, clearly. If you actually do offloading of functions, for example, it's easier to adopt than doing something like Tesseract, which changes everything, including the programming model. So it depends. It's good to examine both in research, but for adoption purposes, it may be good to go little by little. Row clone is easier to adopt, and by violating the timing parameters, you can get mostly reliable row clone. You can design a compiler for it. You can even ship a product with it. I don't know if you'll make profit, but it's possible to do that with row clone, for example, right? It's a relatively simple thing. Existing DRAM chips can do, but there's a lot of adoption issues at the higher level. I think the biggest adoption issue is the mindset issue, actually, because people don't think memory-centric way. And that needs to be changed over time. So I think in the end, the entire stack needs to be revisited with a memory-centric mindset, but maybe it's good to consider these adoption issues to get there step by step. So I'm going to talk, we've done a lot of work on adoption also, like MIMDRAM is actually, or SIMDRAM, their adoption works. But we also did some work on near memory processing adoption. This is work that we did with NVIDIA some time ago. And the idea over here is if you want to offload a GPU kernel, there are some memory intensive portions and there are some compute intensive portions. And if you have some near memory GPUs, very small, relatively small GPUs in a 3D stacked logic layer, you can offload some of the warps to those near memory GPUs, memory intensive code. And compute intensive code executes in the big GPU. And we have a way of doing this completely transparently to the programmer and the data mapping mechanism. So this is one of the older works. And then we also looked at how to enable programming. I'm not going to talk about that, but maybe some of these papers can be discussed. I'm going to talk briefly about SimplePIM, the software framework to enable that. In real processing in memory systems, we developed it for the UpMem system, which is a near memory processor that you can actually program and that you can get real results for. So we worked a lot on that UpMem system. I'm going to mention some of these other works later on, but this is a programming framework for that, but it's applicable to other near memory processing engines also. And I think its principles are applicable more generally too. And also there needs to be some mechanisms to decide what to offload where. And this is this Onur work develops a methodology and a benchmark suite to decide where to offload what function. What is your bottleneck, basically? There's a lot of analysis of code that Geraldo did. I think he analyzed more than 300 applications and 77,000 functions and looked at different bottlenecks. So it's good to develop methodologies. This is not automated yet, but automating it is a good direction also. And there's more work that looks into how to offload functions to near memory processors by taking into account the data movement issues also. Coherence is a mess. There's not a lot of work in this area. It's not an easy area also, as some of you may recognize. But this is one of the works over here that looks at how to design coherence mechanisms that are efficient for near data processors. I'll not talk about that. Synchronization is important. There are mechanisms that you need to support synchronization inside near memory processors. I think this is probably the most hairy issue, which is virtual memory. Coherence is a close second, let's say. But virtual memory is a mess. It has enabled easier programming in single core systems and then multi-core systems. But it's becoming a big burden in existing systems. So how to do virtual memory is still an open question. Okay, we've developed a lot of evaluation infrastructures also. Some of these you have seen. We've been developing RAMlater 2.0 and more recently Virtuoso. I think that they need to support more and more near memory or processing in memory mechanisms. And if you're interested in like a thesis that covers a lot of aspects of processing in memory, you can look at Geraldo's thesis. This is his PhD thesis that he defended in 2025. And this covers actually a lot of adoption issues across the stack. Okay, let me talk about SimplePIM very quickly. Here, we wanted to simplify programming, basically. And even on a system like UpMem, which is somewhat simple to program, I would say. It's not the hardest thing to program in the world. There's still mechanisms that you can use to make programming easier. Essentially, the key takeaway is there are a lot of things that a programmer needs to do to take advantage of processing in memory. Real processing in memory. And that's one of the benefits of having real processing in memory hardware, because you can study issues like this programming much more easily. For example, the programmer needs to distribute data across memory banks. Each bank is a multi-threaded processor in this case. It needs to manage data transfer between the host and the PIM cores, between DRAM banks and PIM scratchpad. This is particular to UpMem. So there's a DRAM bank that has data, and then you need to move the data to a near memory processor. That's the way they decided to implement it for practical reasons, various reasons. Not necessarily the best way of implementing a near memory processor, but they did it that way because they were limited in what they could manufacture. And essentially, there's a lot of data movement, data orchestration that you need to do. You need to launch kernels, you need to synchronize properly between threads, and more, essentially. You need to decide how many threads you run, etc. And this SimplePIM framework provides a high-level programming framework for real PIM hardware using commonly used techniques like map, reduce, zip, and also collective communication mechanisms. And it implements this on the UpMem architecture and evaluates different workloads. And essentially, it reduces the lines of code, and it also provides higher performance than hand-optimized code. So that's the advantage. And this is also openly available. I'm not going to go through the details of it. Basically, the key idea is enable a high-level programming framework such that the programmer is spared from low-level details. And this requires some management mechanisms, some communication mechanisms, and some processing mechanisms. And this also enables code optimizations using compiler, because compilers actually can take advantage of the high-level mechanisms that are introduced. So there's a lot of compile code optimizations that are enabled that contribute to the performance improvements. There's a lot more in the paper. This is one example. This is a histogram program that you can write on UpMem using the UpMem software development kit. Looks a bit dirty. And this is the simple PIM histogram program. Less dirty, let's say. You can make it even better, let's say. And these are some of the results from the paper for some of these programs. Okay, I will not talk more about this, but basically, the question is, can we do better? And Geraldo's data parallel framework actually does a better job. There's more to do in this area to ease the job of the programmer, because the programmer still needs to do a lot. But as you ease the job of the programmer as much as possible and open source these frameworks such that many folk can contribute to it, you can do, hopefully adoption will be easier and easier. Ideally, the programmer doesn't need to do anything, right? That's why we develop compiler mechanisms also. But it turns out that's not that easy to get the best performance on, right? There's always this fight between people who compile and people who hand optimize. And programmers who hand optimize claim that they can always do better than a great compiler. And compiler writers who write the compiler, smart ones, always believe that they can do better than the hand optimized programmer. Right? It's hard to believe both can be true at the same time, but both can be true at specific points in time for, different points in time for different workloads also. In the end, it's good to try to do both, right? Enable both. There's one thing I will mention. There are also interesting security issues that are related to processing in memory. There's no perfect answer to this. Basically, the questions are, does PIM make security better or easier? Does PIM make security worse? There are many interesting questions over here. And one of the things that, for example, does processing using memory make RowHammer worse or RowPress worse? And Ismail showed in his recent work that, what did you call it? PUD-hammer? Yeah, processing using DRAM hammer. And he showed that basically RowHammer, the effects of RowHammer becomes worse if you are able to do consecutive or simultaneous multi-row activation, right? Which is really the core of processing using memory mechanisms. So this is an example where PIM actually makes security issues worse. In this particular case, processing using memory. But there are also cases where processing in memory can make security better or easier, right? For example, homomorphic encryption implementations can be accelerated significantly. We've done this with UpMem system. This is a paper that Harshita led over there in the back, so you can ask her questions related to it, and Mayank. And there's more work in this area that has been done since then, both on UpMem and also with storage. And then there are also other questions like, does PIM make some of the security issues that we know of worse? And this is Nisa did this work, which was published last year. Where is she? Missing in action. Okay. And basically, PIM makes both PIM, processing near memory, and processing using memory mechanisms make covert and side channels much worse because they bypass the caching mechanisms, right? You have covert and side channels that happen because you access main memory, and people have proposed mechanisms to exploit it. And usually, you need to bypass the caches in some way to enable that sort of side channels. And processing using memory or processing in memory happens in near memory anyway. So that actually amplifies the covert and side channel. So it's very interesting ideas. And I have a talk on this if you're interested in looking at what is going on here. Okay. So adoption issues are actually very interesting. So PIM security is related to adoption, actually. No question about that. But workload studies, we've done a lot of workload studies. I'm not going to go over all of these. We've gone on some of these. But we've done a lot of workload studies over years. And one of the reasons is to show that there are a lot of workloads that could benefit from this. This is not a complete set. But databases, for example, benefit a lot from processing near memory and also processing using memory. And we've seen some other things like genome analysis, which I'm not going to talk about today, but you may see some of the papers over here. And we've also done some real, this is actually one of the earlier works that we've done on real systems that have FPGAs near memory. And we've shown that you can accelerate both climate modeling and also genomics, pre-alignment filtering type of applications with these FPGAs that already exist in near memory. So it's good to do these workload studies because they are part of the adoption, in my opinion. Okay, I'm getting close to the end. There are a lot of PIM tutorials and workshops. There's a lot of material on this topic. So if you want to do research in this area, so we were holding, for example, some real PIM tutorials where we discussed UpMem type of architectures and also broader processing near memory and processing using memory ideas. And there was a tutorial on programming, hands-on programming of this. More recently, we've turned this into workshops and tutorials together. So a lot of people in the community participate. Last one was held in HPCA. Ismail is a lead organizer of this. And he's happy to hold it further. He's going to hold it on S+, or we're going to hold the S+, and also, what is this, ICS? Okay. So if people are interested in contributing, just let us know. And there's also a tutorial on DRAM vendor and RAM later that Nisa and Ataberk are organizing. So infrastructure, so this sort of thing is also important, especially when you have new paradigm, right? It's very difficult to change. So you need to build a community that actually does more research. Today, if you look at architecture conferences, there are a lot of works that are on near memory computing, not as much as, or processing in memory, I should say, not just near memory, there's also using memory, but processing in memory. There's a lot of works. It's very different from when we actually started, or when we were trying to publish some of our works in 2013. Roclone, for example, was rejected from ISCA in 2012. So we had to publish in Micro in 2013. So there are a lot of these stories. Today, there's still a lot of rejections, but there are a lot more works in the architecture community. So that's the good part. But there needs to be more open sourced to enable these things better. So if you want more, there's what I mentioned that my micro keynote talk last time. So open sourcing also helps. We open source a lot of these. You can find a lot of these tools online. And that's one of the reasons why we open source things, to enable the community to build so that we can actually enable this sort of change. I think it's not easy if everything is closed source. In fact, I would encourage everybody to open source their work because that's also good for open science in the end. If you don't open source, then there's always this question, does it really work? Okay, any questions? I'm going to conclude. Okay. So let me summarize. I think changing a paradigm is not easy, and that's what we're trying to do with processing in memory. People tried to change the paradigm. I think I have given this analogy before, right? Copernican revolution did not happen overnight. It took 200 years or so. Maybe more, actually more. It took a lot of bright minds, actually. Copernicus is not the one who enabled this revolution. He couldn't fight the fight across against the big power structures of the time. You can guess who they may be. Who wants the status quo not to change, for example, at the time? Yes, take a wild guess, you will figure it out. Okay, but it took a lot of smart people, and eventually after Newton, it was able to, let's say, take hold. So in this case, long-standing and entrenched dogma had to be overcome, right? People believe that the sun revolved around the earth, and that was it. I see actually a lot of things that we do as dogmatic also in our systems today. Dogma is here, processor-centric, right? There are a lot of things that we do that's actually like that, and it's very hard to change things because it has become dogmatic almost, right? And also maybe there's a lot of other stuff that comes into it. Clearly there's business that comes into it in this particular case, right? It's actually interesting to draw the analogy because there was a big business that people were running also that didn't want things to change because of Copernicus, etc. But anyway, essentially, I think we need to overcome the dogma. We need to change this paradigm. This can enable many benefits. Not all of are quantifiable or predictable, right? It's very hard to quantify everything that's possible. And it will not happen overnight. And also, we don't replace the dogma with another dogma. right? The key is basically being scientific. In this case, clearly processor-centric paradigm has its benefits, and there are some parts of a workload that cannot be executed near memory or inside memory. No question about that. So you really need to be heterogeneous. That's why in all of the works that we've discussed, there's heterogeneity. That's a part of it. There are some parts of a workload that can be executed with the current paradigm, but maybe the current paradigm needs to change also to adapt to be specialized to those parts of the workload, right? So in the end, you have specialized heterogeneous acceleration mechanisms that exist, but it will not happen overnight, clearly. So essentially, memory can be designed as a combined computation and storage substrate. And I've given you a lot of examples over here that can lead to orders of magnitude energy and performance improvements, either standalone or collectively. And perhaps the most fascinating one is that unmodified DRAM chips are already capable of computation. So if you actually go and modify them, maybe you can do a lot more. So there's a lot more to do in this area, a lot more exciting research to do and efficiently enable. And I think we need to do the research and design across the computing stack. So there's a lot of opportunity, including theory. That's probably the weakest part that nobody's doing research on. I think theoreticians probably need to look more into building a more data-centric or memory-centric theory of computation. That's not happening as far as I can see. And also, this requires a proper mindset and infrastructure shift that cannot happen overnight. It requires a lot of effort, basically. I like this picture because I think this is a machine. This machine works based on some principles. And this machine is doing some things very efficiently. And it's not using the principles that, as far as we know, that we are designing. We're basically basing all of our computers on, which is the processor-centric principle, right? It's combining communication, computation, and storage in some way, right? That we don't quite understand. The neural networks are based on this, but they immediately do something different from what this machine is doing. They're inspired by this, but inspiration doesn't mean that they're applying the principles that are applied over here, right? And if you look at an AI accelerator today, for example, yeah. Okay, it's good to think about it. That's why people have been developing neuromorphic computing, but even the neuromorphic computing mechanisms need updates because they've been stuck in some paradigm for a long time, in my opinion. Okay, maybe I'll conclude with my more recent analogies. Does anybody know what this is? Let's see. No? Some people know, but they cannot talk because they may have seen it before. If you haven't seen this slide before, have you ever been to this place? Probably not, because you would have remembered. This is called the Gateway Arch in St. Louis, in the heart of the United States. Now, why would anyone go to the heart of the United States? That's a different question. But this was in St. Louis, Missouri. Now, this is actually a very interesting architectural wonder, I would say. It was designed by an architect. And there's actually something on top here. You can go up to it. And there's a tram that takes you up and that takes you down on both sides. I rode that tram recently because I had to go to St. Louis. I was complaining, why do I have to go to St. Louis? But in the end, it was good. So be open-minded. Open-minded is good, you know. I immediately realized my mistake after going to St. Louis that I shouldn't have complained. Although it is a pain to get to compared to New York, for example, or, you know, or Washington. Anyway, this structure is very interesting for that reason. And also another reason, apparently US presidents are not allowed here because they cannot be protected over here. You know, that's one of the most important things to do, protect the US president. Okay. Okay, anyway, why am I telling you this? First of all, this required money to complete. Somebody needed to put money. It's like bridging. That's why they put it in the heart of the United States, so that they can bridge the different parts of the United States, let's say in 1960s. We're talking about 1960s over here, 1950s, 60s. It required a lot of money to complete. Some people may consider it a waste. Maybe it's a paradigm change, right? Okay, that's one reason I'm telling you this. The other reason I'm telling you this is the architect. He was a leading architect at the time. And he did a lot of things, actually, including IBM T.J. Watson Research Center. Does anybody know where that is? I've been there also. I don't complain when I go there, though. a nice place. Okay, but from now on, I learned my lesson. I'm not going to complain wherever I go because there's something to be learned regardless of wherever you go. Okay, so I learned about this story. More importantly, this architect was an enabler, I would say, because he enabled this thing, which is probably an even bigger thing. How many people know what this is? Yes? Exactly. Have you been there? Not yet. Okay, you should go there for sure. And you should never miss the opportunity to go there, especially if it's free to travel there. Okay, basically, yeah, this is the Sydney Opera House. How many people knew about this before it was said? Probably a lot of people over here. So you can see that it's famous. This is actually an architectural wonder of its time. It was very difficult to build. The architect, unfortunately, was fired apparently before it was built, and he never got to see the final product because he asked for more money, for good reason probably, because it's not easy to build this thing. It's an architectural wonder. It takes an enabler to build this thing, right? It's similar to the architecture. Right? Nobody designed something like this. It was a paradigm shift, let's say, in architecture. It cost a lot of money, but you can see that maybe it amortized its cost, right? So many people visited it so many times, and it amortized its cost over many years. I see a paradigm shift in computing in a similar way. It will not be free. It will cost a lot, but it will amortize its cost over time. And that's what really matters. Anyway, the other important story over here is that this architect enabled it. A jury, without including him, discarded the design of the architect who wanted to design the Sydney Opera House, Utzon. And Saarinen was a champion of the design. He basically saw some quality in it, and he championed it, and he convinced everyone that this is what should be built, as opposed to some, maybe, I guess, whatever was in the competition. Right? That's the importance of an enabler. Right? I think people should be more enablers than disablers, especially with new ideas, with potentially big ideas. They should give the benefit of the doubt, and they should fight for it as enablers. Right? It's the importance of an enabler in life. Okay. I mean, some people have enabled our research, so I should fund them, but they're not the same kind of enablers. Reviewers should be enablers also. You know, certainly funding is also good to enable. This also shows that a lot of people are really interested in this sort of thing, like this sort of paradigm-changing research. Okay, I'll acknowledge my students also, some of whom you have seen, some of whom will be your mentors. So if you select Ismail's papers, make sure you learn a lot from him, for example. Okay, I'm going to skip these because we're done. Maybe I'll leave you with this one. Okay, I still have 5 minutes left, but I'm not going to cover the 5 minutes. Has anybody read plays from Bernard Shaw? Do people know who he is? Yes? No? George Bernard Shaw. Okay. He's an Irish playwright. He won the Nobel Prize for his plays. I read several of his plays. Pygmalion, for example, I'd recommend to everyone. It's a beautiful one. Anyway, I'm not going to talk about that, but he's a mastermind of literature and writing. But he also has these two quotes that I think are really important. So the first one says, you could adapt man as a person if you don't like man, but that's what he's referring to in the old language. The reasonable person adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself or his principles. Let's change that to himself to principles, right? Therefore, all progress depends on the unreasonable person. I like this. I think a lot of people don't realize it, but people who have changed how things are done are somewhat unreasonable. They stick for their principles, right? So it's good to think about that. And I think there's another thing over here. Progress is impossible without change, and those who cannot change their minds cannot change anything. And I see a lot of this also. This is in reference to a lot of reviewers that I see, which we didn't get a chance to talk about, but maybe we'll talk about. But it seems like reviewers need to be taught some of these things so that they can understand how important it is to enable some potentially disruptive ideas that may be harder to accept compared to a small incremental change to an existing system. That's easier to accept, of course, right? Of course, I incrementally change the system, things become better, I can evaluate it, evaluate the heck out of it, because I can do it because of the existing system, right? But the bigger thing, that you change everything or a lot of big things, maybe that's a good thing to do based on a principal perspective, and you may not be able to evaluate it easily, right? Okay, I will stop here. We have 3 minutes, but we don't need to take any questions since I've covered memory-centric computing in 2 lectures. But we'll see more of this in this course. Any burning questions? Okay, I'll let you guys go. I'll see you next week.